Now we're going to look at how we can find the derivative of different log functions. So the first box that we have here is the regular log. If I want to take the derivative of log with any base of x, the derivative would be 1 over x ln of a being your base. This is for when you have just an x here. When you have anything besides an x, we're going to use the second one, which incorporates the chain rule. So the derivative of a log with a base a of f of x, some function, is equal to 1 over the function times the ln of a, which is your base, times the derivative of the function. Okay, so you can use that idea for the first one as well, but when the derivative is just 1, you don't really need to multiply by 1. Same thing goes for when you have the ln. So the derivative of the ln of x, when it's a plain old x, is 1 over x. The derivative of ln of a function is going to be 1 over that function times the derivative of that function. And again, here we're using the chain rule because the function that we have has a derivative that's not 1. So let's look at a couple of examples. So here we have the derivative, or find the derivative of y equals log base 2 of x. So if we have log base 2 of x, we can say that the derivative, y prime, is going to be 1 over x ln 2. So because we don't have another function in the parentheses, we just have x, we can use that first version. So I'll go back real quick. We can use the top here because it's just x. So 1 over x ln of the base, and our base was 2. So here's our derivative. Whoops. Okay, for number 2, we have a function inside, so we don't have just an x. So we're going to need to use the chain rule. So we're going to have to do 1 over that function, ln of the base, times the derivative of the function. So we get y prime equals, so we're going to have 1 over the function, so 3x squared plus 5x. So I'm going to put that in parentheses. And then it's going to be times ln of the base, so the base is 6. And then we're going to multiply by the derivative of our function, which is 6x plus 5. So just to kind of clean it up and write it a little bit nicer, we're going to have 6x plus 5 over 3x squared plus 5x times ln of 6. So you can, instead of writing the 1 on the top, if you know that it has a derivative and you're multiplying by the derivative, you can just put the derivative right on the top since it's always going to be multiplied by 1. Sometimes things can simplify. Here they can't, but if something could simplify with the top and the bottom, you want to try to do that as well. So here we're going to look at the ln version. Okay, so the derivative of y equals ln of x, so y prime equals, since we have just this x here, again, let's go back to the two scenarios here. When it's plain old x, you're just going to have 1 over x. So our derivative would just be 1 over x. For the second one, what's inside is not just an x, it's another function. So again, let's just kind of look back at this. So we have the derivative of the ln of a function is 1 over the function times the derivative of the function. And again, you can skip the step of putting it as 1 over if you want to just put the derivative on the top and the function on the bottom since you're multiplying them anyway. I'm going to just show both just so you know where I'm getting things from, but usually I'll just kind of skip that step. So I have 1 over x cubed plus 1 times the derivative of what's inside, so 3x squared. So I'm going to just clean that up, and I have 3x squared over x cubed plus 1. And there's our derivative. Okay, so let's look at another example here. So find the derivative of the ln of sine x. So we're going to have 1 over sine x times the derivative of sine x, which is cosine x. So if I write these together, cosine x on top and sine x on the bottom, cosine over sine is cotangent. Okay, so here we're going to differentiate, so find the derivative of the square root of the ln of x. So again, I'm just going to always write, when I have a square root, I'm going to change it so it's a exponent. So I'm going to make it ln x to the 1/2, just to be easier for when I'm finding the derivative. So here, the ln is on the inside, so I need to use the chain rule. My outer function is something to the 1/2. The inner function is the ln. So if I find the derivative, f prime of x, I'm going to take the derivative of the outer function, so that's going to be 1/2 ln x to the negative 1/2 times the derivative of the ln of x, which is just going to be 1 over x. So just to kind of, again, clean it up and write it a little bit nicer, I'm going to get 1 over 2x square root ln x. Okay, so now we're going to look at one that maybe is not so nice, and I'm going to actually show you two ways that you can do this. I'm going to show you the, I guess, way that you might think to do it, and then I'll show you kind of like a little bit of a shortcut way. So here we have to find the derivative. Okay, again, we're doing the derivative of an ln function, so it's going to be 1 over the function, x to the 4th sine squared x, times the derivative of what's inside. Well, what we have inside, we really have, I'm just going to write this a little bit differently. So ln of, this is like saying x to the 4th and sine x squared, right? So sine squared x is the same thing as this. So we really have a couple of things going on here, which kind of makes this annoying to find the derivative of, because we have the product rule, since we have x to the 4th and sine x squared, and the sine x quantity squared, we have to use the chain rule. So there's a lot that's going on here. So let's start with the product rule. So we're going to do the first. So that's going to be x to the 4th times the derivative of the second. So the derivative of sine x quantity squared is going to be, the outer function is the squared, so it's going to be 2 sine x to the first power times the derivative of sine x, which is cosine x. So that's first times the derivative of the second. Then we have to do plus the second, so that's sine x squared times the derivative of the first, so the derivative of x to the 4th is 4x cubed. Okay, so if we were to smush this together, so we're going to get 2x to the 4th sine x cosine x plus 4x cubed sine squared x over x to the 4th sine squared x. Okay, so technically you could leave it this way, right? You found the derivative, you plugged in everything, and that's where it's at. But if we wanted to simplify this a little bit further, it's kind of annoying, but we can do it. We can look to see what everything has in common, right? So if you look at the top, there's two terms in the top, and you have the expression on the bottom. They all have some type of, oh, let's actually factor the top first a little bit. So on the top, we have the 2 and the 4, so we could pull out a 2. We have x to the 4th, x to the 3rd, so we can pull out a 2x to x to the 3rd. We have a sine x cosine x and a sine squared x, so we could take out a sine x. So we're left with x cosine x plus 2 sine x over x to the 4th sine squared x. So from here, we could simplify with what we pulled outside. So the x cubed is going to go away, and this x to the 4th is just going to become an x. This sine can go away, and this sine squared is just going to be sine. So let me change colors. So y prime. So right now we have the 2. So I'm just going to distribute it in. So I've got 2x cosine x plus 4 sine x over x sine x. So again, that's better, but it's still not fully simplified. So if we wanted to fully simplify this, we could break this up into two different terms, because we have two terms on the top and they have that shared bottom expression. So I might break this up. So I'm going to do that actually. I'm going to do 2x cosine x over x sine x plus 4 sine x over x sine x. Okay, so I didn't change anything, I just rewrote it a different way. Okay, so when I do this, I can cancel out the x's here. I can cancel out the sines here. So on this left term, right, I have 2 cosine x over sine x, and cosine x over sine x is really cotangent. So I can write this as 2 cotan x plus, and I've canceled out the sine x's, so 4 over x. So here is my, oops, sorry, pretend that I didn't do that. That is my most simplified derivative. Okay, so it was kind of annoying to get to. It wasn't anything that was very difficult. It just was a lot of steps and you had to factor things out. Now I wanted to show you another way that we could do this that's a little bit easier. So if you notice, let me start a new page. If we notice the original function, right, it was ln of x to the 4th sine squared x. If you remember your properties of logs, when you have the ln of something that's all multiplied together, multiplication goes hand in hand with addition. So you could break this up. So another way that we could write this would be y equals ln of x to the 4th plus ln of sine squared x. And if you remember again your properties of exponents, the exponent can go, not exponents, properties of logs, the exponents can come down in front. So I can rewrite this as 4 ln x plus, so remember that sine squared x is really sine of x squared, so this would be 2 ln sine x. So we just rewrote the original problem to be a lot nicer, so when I go to find the derivative of this, I don't have to do all of that crazy product rule and all the stuff. I have everything set up for ln's. So now when I go to take the derivative of this, I'm going to have 4, which is our constant, is going to stay. The derivative of ln of x is just 1 over x, plus the 2 is going to stay. The derivative of the ln of sine x is going to be 1 over sine x times cosine x. So if I put it all together, I get 4 over x plus 2 cosine x over sine x, which we said before was just cotangent, cotan x. So I get the same answer in a shorter amount of time and shorter steps because we recognize that we could use the properties of logs in order to expand this and write it in a different way. Okay, so we're going to look at one more. So on this one, okay, we could use the quotient rule because we have a fraction here. However, because it's the ln of the entire thing, we could use our properties of logs like we did in the previous example. When we have division, we really have subtraction. They go hand in hand. So if I have the ln of x plus 1 over the square root of x minus 2, I can rewrite this as the ln of x plus 1 minus the ln of x minus 2 to the 1/2. So just rewriting it. Again, the exponents can go down in front. So I'm going to have ln of x plus 1 minus 1/2 ln of x minus 2. And now I can take the derivative of this. The derivative of the ln of x plus 1, well, that's going to be 1 over x plus 1 times the derivative of x plus 1, which is 1, so I don't need to do anything with that. And then I have this 1/2 here times the derivative of ln of x minus 2 is going to be 1 over x minus 2 times 1. So I'm just going to rewrite this as 1 over x plus 1 minus 1 over, and I'll just write it like 2x minus 2. Okay, so you could leave that as your answer if we wanted to combine them together. So this is, I'll just put like y prime so we know that we're doing the derivative here. If I wanted to combine them together, I could get a common denominator, right? So like I would need an x plus 1 over here and here, and I would need a 2x minus 4 here and here. So if I multiplied that out, I would get 2x minus 4. Don't forget to distribute this negative if you're going to do that. So this negative 1 is going to the x and to the 1. So that's going to be negative x minus 1 over that common denominator. So I'm just going to keep it as that 2x minus 2x plus 1. And then just combine like terms on the top. So I'm going to get x minus 5 over 2x minus 2x plus 1. So I think that this would have been a lot more complicated if we did the quotient rule, but because we recognize that we can use the properties of logs, it's a lot easier to expand it and rewrite it and then find the derivative that way. So this last example, we are going to find the equation of the line tangent to the curve y equals ln of 3x minus 8 at the point where x is equal to 3. So remember, when we're finding the equation of the tangent line, we have to first find the derivative. So y prime is equal to, the derivative of ln of 3x minus 8 is going to be 1 over 3x minus 8 times the derivative of 3x minus 8, which is 3. So I have 3 over 3x minus 8 as my derivative. I want to find it at the point where x is equal to 3. So I'm going to find the derivative at 3. So let's plug 3 in for x. So I get 9 minus 8. So I get 3 over 1, which is 3. That is my slope. Now I need to use the point and the slope to find the equation. I'm not given the point, but I do know that x is equal to 3. So if I plug that into the original function, so y equals ln of, if I plug 3 in, I get 9 minus 8. I'm going to get the ln of 1. And remember that the ln of 1 is equal to 0. So the point I'm using is 3, 0. So when I go to find my equation of the tangent line, I have y minus the y value of 0 equals the slope of 3 times x minus the x value of 3. And if I want to solve for y is equal to 3x minus 9.